Thank you. So welcome. I'm sure you had a good time so far, and hopefully I will keep you entertained. How many people here use Java at all? Excellent. Otherwise I'm going to say leave the room. Okay. Right. So let me talk about let's talk about me quickly so you see where I come from. So I work for IBM, been working for IBM for a long time. I started in the Java space when Java was, as I said, before it was one. Tiny thing right at the beginning. And ever since then, pretty much my life has been around JVMs and associated tech and a few other things, right? And you'll find me floating around the open source community, you see me in OpenJDK and places like that, right? But one of the things I get really interested in is where are we going next? What are we doing next? Where's it all going to go, right? So this talk, this talk may seem to you to be about JVMs and the Java, and I use those interchangeably. From my point of view, Java is the programming language that runs on the Java virtual machine, but it's the virtual machine that is the star for much of this. And I talk about Java and JVMs interchangeable here. Whether the future holds for Java to be the same as it is today or completely different, we'll find out. But the VM, the bit underneath, is the bit we're going to talk about, is definitely, got good reasons for continuing. But actually, what we're realizing is it's not so much the technology that has to change, it's us as people, how we think about problems that are going to change. And I'm going to talk through that as well, right? It's about solving problems differently because we have new and different types of challenges. And they are different. So we've got cloud. People talk about cloud. What are we doing in Java to make it better for cloud? What are we doing in the data analytics space? What are we doing to help Java programmers do things better? What are we doing in machine learning? And what are we doing beyond all that? The interesting thing is all of this tech, so much, cloud is probably the last tech that we'll have where you can say it's the same as the old tech, but it's just slightly different. There are different drivers. But the new things are changing the way that we have to look at computers and how we solve problems. And that means we have to do things differently in the VM and stuff. So actually, as I say, most of this talk is about underlying this is, well, what's your future going to be like? What do you have to learn? And what do you have to do differently? So we could start with, what are you thinking about today? What is it that's on your mind, right? Now, if you're in the Java space, now, I don't know how many of you are students, how many of you are professionals, but if you're involved in the Java space, then there's a whole bunch of things that are going around at the moment, So are we thinking positively about any of these things? Are we thinking about, are you still using Java 8? Are you looking at what's coming in? Well, I say at Java 9, but Java 9 is just gone. So are you looking at what's in Java 10 or 11, right? Are you trying to figure out how this release process is going to work? All those sorts of things. Are you trying to figure out what things like LTS mean? As Java moves to a different way of releasing software, what does it mean for you? What does it mean for the companies you work with or the companies you could work with? Right? What about modules, Java module system? How do you get your head around that? And if you've spent any time writing Java, you'd have done it one way and now you're being asked to do it a different way, right? And there are other bits and pieces, right? And it's all, well, are you thinking about Java that way? Are you positive? Maybe you're not. Maybe you're not positive. Maybe you're going, well, there's this really tiny Java thing called Java ME, and then there's this Java SE, and there's this big thing called Java EE. It's massive. It's so much stuff. We just don't want to get involved in that. You might be looking like this. You might be going, there's this big wrestling match going on between Java EE and Spring, and micro-profile new stuff, and yes, all this fighting, and who cares, right? Maybe you think of Java like this. Maybe you're going, yeah, Java's old. It's just too hard to catch up, right? Because everybody else is faster and better. And the funny thing is that in many ways, how you look at it, that might be true. You might look at the technologies and you can point at situations where you can say, Node is better, Ruby is better, Python's better, but there's slices. Right. One of the things that you see here is actually, It's not about being good, the best at everything. It's about being good at everything and being able to change and take your users with you. And that's what we're going to show you can do with the JVM. So we tend to think about what we're doing now, the technology. We don't think about the future because you're trying to solve real problems now, right? We're just looking through that, okay? And in the Java space, you might have a wider view. You might be looking at the politics, the business. Why is it that IBM's open sourced its technologies? Why has EE moved from, why has Oracle contributed it to Eclipse? What's happening in the microprofile space? Why does it exist? Right? Is Spring the right answer? Should we be doing stuff with Spring? And you might be thinking these things. And I hope you are, because it means you're leveling up and not looking at technology as just a tool. You're looking at the ecosystem and starting to understand the choices that get made. And the more you can do that, the more you can predict what will happen next, right? Right. So questions like, should you be using Java or something else? Well, as I said, there's point solutions and there's the bigger picture, right? What should you be doing, right? So let's step back. Let's look at why any of these decisions get made. What drives us? As technical people, people who are writing code, we can be excused for forgetting that underlying this is business. People make money, whatever it is, right? You obviously know that IBM and Oracle sell things, and they make money, but obviously you might look at open source communities, but you have to ask yourself, who pays for people to contribute in open source communities? It's all about business, right? It's all about this word, economics. Economics, faster, cheaper, easier, better, whatever. How do I make more money, right? That's the underlying driver, and we have to remember that, and that will flow up as I carry on. So Java innovation, right, has been driven by economics, and the majority of our years in Java have been about improvement in performance. It's about taking Moore's law, right, which is just this increase. I can get more transistors onto the chip than I did last year, and it won't cost you any more. It comes for free. So all the software is working out how to give you benefit from that. And that's what we've been doing. For years and years and years, we've been working on trying to make sure that Java has been the best vehicle for delivering the value of your investment, right? And to do that, we built this walled garden. We took Java and we said everything is better if it's inside Java, if it's inside the heap, right? Interop with other things isn't optimal, so let's put everything inside. Let's have a Java ecosystem. Let's have a concept of Java applications that are all about being the thing, and you don't talk to anything else, right? And we've been really good. I cannot point at anything else that's anywhere near as good as what we've achieved. As a community of vendors and an open source community, the collaboration that we work together through standards, processes, and competition has given us the best, right? The fastest runtimes, right? They scale better than anything else. We have the best garbage collection technologies, not just IBM, Oracle. We have invested millions of dollars, thousands, tens of thousands, hundreds of thousands of man years into this tech, right? We have solved problems that other language environments have not tackled, right? And that's really good. And it's been fantastic for Java applications. Okay. Trouble is, that innovation that we've done, where Java has come from and what happens in Java, has mostly been driven by somebody else, right? It's all mostly about Moore's law. And then we had this problem, where was it? 2010, I think it was, where Moore's law broke. You may have heard about it, where people said, we just can't get more transistors on the chip in a way that you can make use of in a single process. This chart, as you can see, continues because when it was produced, there was the expectation, I think it was produced about 2010, there was an expectation it would go on forever. And then it broke. And so we spent a lot of time in Java figuring out how to make more use of multi-cores, which is why things like Lambdas and the streaming APIs occurred, because innovation was needed to make use of that technology. So it was driven by physical changes, for the change of silicon. And the other thing that's recently got to us is this one. Aha, we went, wouldn't it be really good if you could just get computing power when you felt like it? And that's what we did. We gave compute on tap, the cloud. Right? Faster, cheaper, easier, better. Right? The interesting thing is, it's all the same, right? It's economics. Economics rules the world. Economics rules the future of Java, right? Except for things have changed. Now, as I said at the beginning, cloud is one of those places where the economics are different. I'll talk about in a second. But it's probably the last time that we're going to see this sort of change. So cloud has given us economics in your face. You may not have seen it before, you may not have thought about it, but right now, cloud says you have to think about how you create applications differently, because if you can buy compute power is now currency. It's that easy. Especially Bitcoin, yeah. But you can go to Amazon and you can spend $100 and you get $100 worth of compute power. Right? When your $100 is up, you don't get the compute anymore, right? And it's all around this little symbol, dollars equals gigabytes per hour. That's what the economics is presenting to us. That's how you buy compute, right? And if you're a Java programmer, you can think of it like this. The size of your heap is now worth money. So if you can make your heap smaller, then you save money and your company will be very happy, right? And by the way, that's what they want you to do. Now what happens is when people come, when you say, if you're in a cloud business and you need to increase the size of your heap because you've got some dependency or something's happened, well, guess what? They're going to say, your accountant's going to say, well, that's going to cost us, well, we're going to have 1,000 of these running at any one time, so that's, well, we've gone up by $1,000 an hour or something. Okay, that's what they're thinking, right? And the really scary thing is cloud isn't going away. Cloud is big. Cloud is turning up right here. So I don't normally do product pitches, but this one I will do because this is really cool. IBM has this thing called Cloud Private. And what it is you can do these two instructions, git clone and vagrant up, and you can have a Kubernetes cluster with a whole bunch of stuff running on your laptop within about 20 minutes. Right? It's cloud. What the businesses are doing is saying, we want cloud in our data centers. We've seen what can be done on public cloud, we want it here. So the pressures on Java aren't just, hey, can you make it really good in the cloud and can we do it the old way locally? It's like, no, it's all about cloud, right? So you can go get, this is the CE version, but I mean, you can go see what you get. And it isn't rough. These are some screenshots. The point being, the technology is that you can have a cluster on your machine, have it on here, have it in your data centers, bring in the variant types of data compute you've got, put them underneath, press the button, you have compute cloud locally, right? And it can have some really good interactions. It's very professional, right? App stores, the works, right? And that's what businesses want. Right? The trouble is, it means we've got to, from a cloud point of view, from a Java point of view, we have to change the way we're thinking, right? So partly we have to break out of this walled garden that we created, right? But we don't know how to do that. Well, we know how to break out of it, but where should we put the investment? So we've got cloud, which is now, and soon I'll talk about the next steps. But cloud is the obvious one, right? And it's saying we have to change, right? We're saying, hey, we have to go from these old style applications, these long running things. We were all willing to trade off startup time for throughput. We were willing to take time for something to get ready because it didn't affect the economics, right? We wanted long running applications, those big monoliths that you hear about. But to add to that, we now need to add something different. Cloud says, We want short-lived things. We want service-oriented. We want polyglot. And we want Java to play in this space. So if I put up some charts, and I'll try and read through these charts. So the big one, so stylized chart, throughput along the bottom, or number of instances along the bottom, throughput through on the vertical axis. The point being that we used to say we want to be able to scale things as we add more and more services or we put more calls in. We obviously want the scaling to be equal. We don't want any loss. But we're willing to lose performance at the beginning, hence the curve leaning. And we're willing to spend time at the beginning, that big spike at the top, optimizing things that we're then going to... So we're willing to be inefficient to start off with because we gain efficiencies later. And we want one big thing. Well, what Cloud says is, can you make Java not like that anymore, please? Can you make Java so we have multiple little instances? And can you make that line, that attack line, vertical? And can you remove that hump? Why do you want to remove the hump? Because when I'm buying compute power, I have to work out what's the maximum amount of memory I'm going to use. And if I have a big hump in my setup cost, I have got to buy a bigger VM to store it in, even if after that I never use that amount of memory. So big peaks, or any peaks, break the model. So we need this sort of approach. And of course we need it now. Why not? We've been promising cloud for such a long time. So our challenge as a Java community is that we built this walled garden, we had an approach. And now, if you look around, you can say, hey, look, Ruby does it better, Python does it better, Node does it better, for some narrow piece of better. And we need to figure out how to deal with that. And we need to deal with the fact that those things exist. They're not going to go away because they're good places to put your investment. So one of the things that Java has to do is become so much better at playing with others. Right? And this is why, as at the beginning, if you raise your eyes and look at what's happening in the industry, in the Java industry, you'll see why it is that these things are happening. Why is it that we're changing? Right? Why are we going for a faster pace? Why have we got this new cycle of getting Java out? Well, so we can get the innovation out quicker. We put out amazing amounts of innovation, but it takes a long time for you to get it. Other programming languages release very often. So Java needs to be able to release things much quicker so that you can try it and feed it back. Right? And we need more people involved. So if you guys are at a loose end and you want to do some hacking, there are a whole bunch of products you can go hack on and try and play and try things out. Right? There's a whole room for loads of innovation. Right? You know, and so these things that we've talked about, you know, you've seen lambdas and streams. So modules took 10 years to get here. 10 years. Massive amount of investment. Fantastic set of re-engineering. Took 10 years. Far too long. It should have come out very quickly for you to try to get feedback. Right? So what we're going to try and do is ensure that not only is it faster, but there are more variations. So you can now go to Adopt OpenJDK, for instance, and you can get OpenJDK with Hotspot, you can get OpenJDK with J9, you've got all the various open source app servers, they've all got their different values. And all of these are going to be working together as we explore the future, right? And pulling out this stuff, right? So instant things like Docker. Who uses Docker? Oh, come on, you've all got to. If you haven't, you've got to put your hands up by the time this thing is over, okay? Get your laptops out. You have to use Docker, right? Docker is the best way of understanding about containers. Docker has its own performance characteristics that Java has to fix. So we have to fix that. We have to fix the interop between JVMs and Python and JVM and Ruby and those things because that's important too. We have to think about re-optimizing our JIT technology so that we can create a pipe, a shape of performance that matches cloud. We know how to do that, right? We just got to figure out the best optimizations, etc. And there are things like AOT, ahead of time compilation. That was never a particularly large thing on our list because we didn't need to do it because we had really good JITting and everybody was willing to spend the time at the beginning. When you've got Docker containers and you're spinning up services all the time, you want that startup line to be quick as possible. So you can't spend too much time JITting. Because if you spend time JITting, you're not running. So one of the things you can do is you can do a ahead of time compilation. Compile the Java and the bytecode to machine code, store it in the Docker image, ready to go. That's cool. However, it's not the best. So things that we're exploring are things like JIT as a service, which is, well, why don't we take the JIT out of the JVM and stick it to one side, right? And then have your JITting, your Docker image, when it starts up, have this service, persistent service, do the compilation, send back the machine code. You send profile information as your Docker container and multiple Docker containers work. All that profile information goes to a central service so we can actually get even better re-optimization. Right? And some of this is coming out now. This is here. You can get some of these performance benefits in terms of like faster, smaller footprints, faster startup time. So these are just some basic performance figures. So these are my machine. So it was like, how much memory did you take to run something? So in this case, it's a thing called ngrinder. It doesn't matter what it does. It was just a big, fat set of Java code. And it had a point where we knew it was running. So you do this, right? Hotspot Java 8, 577 meg on my machine. I use the OpenJ9 JDK 8, 359. So I reduce the memory footprint just by switching VMs. Right. And it gets even better. Java 8, 577. Java 9, hotspot is caught up, 340. OpenJ9 variant for Java 9, 240. So look, 240 to 570 just by switching to the next version and a new VM. Right? And that's what we're trying to get, is get the stuff out to you to try these things out. Right? And this you can go try yourself. Right? You can go to Adopt OpenJDK, download your favorite JDK or two and play and see what you can do, see what you can measure. But the point is that stuff's coming now. Right? The cloud, scaling, performance profiles, we know how to do that. We're just re-optimizing for a new way. I mean, there's a whole bunch of engineering required. Excuse me, but we know what to do. It's not the big change. It's not going to change your life that much. So this is really where the future starts. What comes next? So there are two big topics, and very interchangeable at a VM level as to what we're talking about. Data analytics, machine learning at the bottom, and something else, which we'll talk about. First thing is, it's all still driven by economics. Data analytics, machine learning. Why do we do that? You know why we're doing it. You can see it in the press. Everybody's saying, I can use machine learning to do something. It gives me a competitive advantage. Right? I can do data analytics to get insight into things. That's a competitive advantage. So it comes down to, so what does the VM can do? What can the VM do, or what should it do to make that easier? Right? The challenge for some of us is that these new problems are not enormously tractable by human beings to think about. If you've written any of these things, if you've tried any AI, machine learning, data analytics, whatever you do, you soon reach this point where it becomes complicated to even think about, right? And this is the challenge for us all, is we're now moving into a place where computing is going to be doing things that we're just not very good at understanding, right? And it's not just never going to change. It's just going to get worse or better. So we're talking about visualization. How do you visualize these big things that you've built? How do you know that they're accurate? How do you know that they're performing well? How do you know that they are right? Right? And our brains aren't really up to doing that. And it turns out actually that a lot of our computer design isn't optimal for it either. And we'll go through that. So first though, because I'd like to set this so that we get the scale, because people go, well, I did a little thing and it's fine, I understand it. But when you look at the big picture and you go, well, what are the scale of the problem we're trying to deal with, right? What is it that machine learning and data analytics, et cetera, are going to do, right? So we know that most of the time, machine learning is about finding reasonable answers, and human beings are involved in trying to guide that solution. It's not always the case, but the majority of cases, there's some oracle that says it's right or wrong, right? So let's about this. So you go, well, what's best? So here's a little tiny example. Let's suppose that we want to organize, we're going to have a little table, we're going to have a conversation around the table. So if you're going to organize a conversation, what are the permutations that you need to deal with, right? So if you've got 3 people around a table, and you're going to go, I want to rearrange those 3 people so that the best, that's my definition of best conversation, can take place. I don't want that guy sitting next to that guy because I know they don't like each other. I know that guy and that guy are really good together. How do I work out those combinations? With 3, it's obviously easy, right? You can put 3 people around, there's 3-way conversation. How many combinations do you have to process to get the best answer for 10 people? Anyone got the answer? No? Okay, well look, here's the answer. So there's 10. Right. What happens if we try to do more? What happens if we filled this room up with everybody and we said, let's rearrange ourselves to get the best conversation? How many permutations do we have to go through? All right. Anybody got that number? No? It's this. Right. So that's the challenge of the scale, right? We're very good at understanding the 3. We can probably just about get our head around the 10 if we write some procedural code to go through to score it. But when somebody says to you, here's the number of combinations that you need to go through to work out what the best answer is, you need help, right? And that's what we're looking for. And businesses know that, right? And more than that, the businesses have been sold on that, on this level of complexity that can bring value, right? And so look, here's some things. I don't know if you can read that, but I'll read some of them out. These are real things. People are doing real things in this space. Tailor responses to the personalities of your customers without meeting a single one of them, right? You know, when you go to a web page, you probably get some adverts that's tailored to your benefits. I buy something at Amazon, the next thing I know I'm getting adverts. Easy, right? But they can do more. Right? Process inefficiencies. Can you measure? How about measuring your deployment processes for code, working out where things are going wrong and improving them? Right? Uncovering patterns, resources, trends, and other competitive advantages invisible to competitors. I don't know what that means, but people are doing this, and they're asking us to provide those solutions. Improve themselves over time, learning from adapting to the world. That's what it's all about, right? Do you know how to design a system like that? Right? And this is the challenge we've got. So we have all this machine learning, which is mostly designed around the fact that somebody is doing the training, right? But it's all about the best. What do you think is the right answer? Get the machine to do that. We talk about bias in machine learning, right? But some people will put bias in because it's a value. The thing is this stuff is incredibly expensive to create because it's all an art. You end up with machine learning, you've invested in something, you have an answer, it works for you. You're going to share that? Not enormously. Right. What we will expect to see, and the reason I'm leading up to this, is how is your life going to be different? So we know from history that if you create a service that is expensive to create, you're going to protect it. Right? You're not going to open source it. You're not going to make it available. You're going to allow people to call it. Right? We also know that these things, because they're expensive, they're going to be run in the cloud. So whichever cloud they're put on, that's where it's going to stay, right? So we know that you, as developers, are going to spend more and more of your time changing the way that you get your data into these systems rather than downloading, installing, and doing things like that, and creating applications. It's all going to be service-based, right? And that's going to, your job will be one of two things. It's either going to be the guy who figures out how to get your data into a form to work with this service, and then this service, and this service. Or maybe you're going to be the other way around. You're going to be the guy producing these things, right? Right. So when that economics, machine learning, data analytics, loads of money's been made, percolates down to what Java developers have to do, what VMs have to do, comes down to these three things, right? JVMs have to be so much better at machine learning and data analytics, which will explain what that means in a minute, right? As a Java developer, you're going to be spending less time writing traditional applications and more time playing with data, thinking about solving problems by changing and manipulating data, more data analytical activities than coding, though it's still coding, but it's not in the same way. And everybody, every developer in the world is going to have to get used to the fact that, those days when you could write your own Pac-Man, that's really cool. That's sort of gone now because you now need to use some intelligent AI service to do something to give it value, right? You want speaking Pac-Man that understands the right things to motivate you. So let's put this into code, because this has all been a bit academic, a bit high level. So what does it mean for Java programmers? So let's some examples of how you're going to have to think differently. So word search. Hidden in this grid of words are almost all of those words. There's one missing. So if you're going to write some code to find those, so I'm going to say to you, here's the grid, here's the words, tell me which word is not in the grid. Right? You're going to go through those things and you're going to write some prototype that says, for every word, go left, right, up, down, left angle, whatever, stick it in a list, and then compare the list with my original list, and which one's different is the answer, and you get that sort of stuff. Yeah, I know where words are, I know the directions, lovely. And you've probably written code that looks just like this. Okay? Right. And the first thing you know is it's not very efficient. So apart from it being loads, you run it and you go, oh, I'm only making use of one CPU because I don't actually think in multi-threaded ways. So the next thing you're going to do, because you're up to Java, is you're going to use some of the streams APIs. So in this case, what I've done is I thought, I'm not going to think of my grid as a grid. I'm going to think of it as a sequence of cells. It's just an array. So my first thing is I start saying, give me an int stream, 0 to however elements. Okay, and that gets me into the world of streams, because I can then do this little bit of modular arithmetic from that number, right, and work out what the x and y coordinates are, and then I have the rest of my crap code. But by doing that, I now get parallelism. That was easy, right? I didn't really have to think about that. But I've still got some gawpy code, length checks and bounds checks and stuff like that, because I have to deal with the fact that when I'm searching, I'm looking for a character, so in this case J, somewhere, I might find it at the edge, and it might not be a complete world, so I have to worry about falling off the edge of the grid, right, because I've found a partial match. So I have to have all this rubbish in there to do bounds checking. So one thing you can do, and if you're a games programmer, you might go, oh yeah, I do that, is you change the shape of your data, and you put a boundary, a bigger buff around your data that's full of nothing, right? So that in fact you will never have a bounds check problem, right? Because it just hits empty zeros, right? And that's really good. That's one way of thinking about solving the problem, away from writing code towards doing data, changing your data. And you can go more. The need to scan left, right, up, down, forwards, backwards, in all those directions, you can code it. But if you think about it, you can turn the coding into offset combinations. So you can just have a matrix of those instead, and then your code gets even easier because you have offsets rather than lots of code. And suddenly your code's so much better because you thought about changing the data rather than changing the code. And that's my point, is that's what we have to do. That sounds, it's all a bit simple. Hello? Okay. That's okay for small data, but of course, we're not talking small data. We're talking billions of characters, right? We're talking arrays with millions of words, right? Multidimensional, things that you can't get in your brain, okay? And words that are so long that having those buffers, even that approach would not work because you'd have to take so much memory to deal with that. So you will be thinking about solving problems by manipulating data rather than writing code. And the first thing you're probably going to do is stuff like this, using clusters. Anybody use any of these clusters? Apache Spark? Okay, yes. So next thing to put on your learning list, clusters. Hadoop, Spark. Okay, take the word grid, break it into bits, push it out to a bunch of machines that do the partial analysis, and then collate the results. Okay? Oh, actually, having said that, what happens if you've got a word that spans the boundary? Well, that'll never get found if you find that simplistic approach. So you might do more things. You might go the extreme. You might break your grid into tiny ones and do little tiny partial matching and having lists of potential hits and combine them together. You're thinking differently about how you do to solve the problem. And underneath all that, well, things are going to change. So the first thing is, if you were going to look at what was underneath any of these nodes, you'd imagine there's a CPU. Where? Yes? Why would there not be? Well, nowadays you might hit one of these. GPU. Okay, so what about these two? These are two new sets of types, well, not new, two sets of hardware types that are coming in more and more in the business space. So ASIC is basically take your solution and codify it directly into hardware, transistors, bake it. And FPGA is like one-up programmable hardware. Right? These will become new ways that you're going to be getting involved with computing. And obviously from a Java point of view, we'll be trying to do our best to ensure it's easy for you, but you have to think about them. GPUs don't work the same way as CPUs. None of this hardware works the same way. So it means you have to work differently. So let me give you another example. So here's a simple one. So you want to write upper lowercasing type code. String dot to uppercase type thing. So you want to do it yourself. So let's just, because you want to, right? So here's an example. You go, I have a bunch of characters, and I'm going to do some code that turns them from a lowercase to an uppercase, right? And you might do this, right? You might go through, this is just what the string to uppercase actually does, but you're basically going to write code like that, okay? You might do the int string version. That sounds a little bit better. I can have an array, and I can have multiple threads, one for every element. I could even do a switch, right? That would be cool. That sounds really useful. I can have a whole list of A to Zs. And you might think that that sort of uppercasing approach, where you could say, well, I'll take every character in my array and I'm going to make a thread, would fit for a GPU, because that's what you're doing in parallel. So let's explore that. So those two bits of code, right, we'll work through it. So CPU thread, so I've got two CPU threads. Watch what happens. And we'll talk about why in a second. So they step off together at the first element. They go down one. Yeah, it's still the same. Right, step 3, this one has found out that its data is W, right? This one hasn't, so it's obviously a different characteristic. It goes on to the next one. And the next step, this one is now finished because it's done its job. That's a step 4 over there. But it's a separate thread. It's processing normally. Right? And then this one finishes. Step 5. Cool. That's what happens. Here's the GPU case. Now watch this. This is different. GPUs. So you've now got a new way to think about this. Because in GPUs, that program counter, the thing that keeps track of which statement you're executing, there's 1 for every single one of the thousands and millions of threads that are running in a GPU. In in a CPU, they're all separate. So your threads can all do separate activities. They never get in the way of each other. But in a GPU, they're all totally linked. One step. So that means that when I do this, they all get to the second step. This one gets to step 3 because it matches. These two are now stopped. They're not processing anything else. They're stopped. Right? It might be that the next thing that gets is this one, step 4, but in which case these two threads are now stopped. Right? And that does its one. These two are still stopped. Right? Oh, this one has a go. Step 7. And then finally step 8 for all of them. Every single thread had to wait the length of time for the whole set. 8 threads, 8 steps. Right? So if you do not understand how to write a program to be effective on a GPU, you're not going to get the mileage. And it's not the same way that you think about CPUs. Right? I always say this, if you don't use GPU properly, it's like driving your car backwards all the time. Right? You get no value out of it. Okay? However, if we can get value out of it, and we can get value out of this, it's significant. There's this step here, there's another one I'll talk about in a sec. So busy chart, but basically the OpenJ9, the Eclipse OpenJ9 JVM has CUDA support in it and will figure out some of your patterns like int streams and work out how to turn that into machine code that runs on GPU. It's pretty limited because we're only at the beginnings of it, but simple things show like sorting. Sorting can go from being very expensive on a CPU to being trivially cheap on a GPU and getting substantial value, right? Because we can get the parallelism. But the point is, this is where everything changes. Up until this point, we've said, you write your Java code and we'll make it work on the hardware. People don't realize just how much hardware change has happened over 20 years. Right? All the new types of new hardware. When processors come out with new instruction sets or advanced instruction sets, the JVM and the JITs hide that from you. Now is the time where that's going to change because you've got to write different data algorithms. The good news is that this is your Java application. Right? Java, you write your Java application, it never runs. It's just a model. We have this thing called the JVM, and it turns your model of an application into something that goes really fast. We turn it into reality. Right? And most of the time that has been transparent, right? Which for a good thing, because if you've got a model, we can translate it into different ways. Right? So the thing is, with this new approach, with this new set of drivers, we can't hide the fact that you have to think differently. So GPUs are doing it, AI is doing it, AI is coming in. Excuse me. GPUs are turning up in data centers left, right, and center, not to play games on, but for you to do business work, right? Because people understand the value. We're working on how do we get the JVM talking to the GPU in a cost-effective way. So there are some JEPs coming around that will help you in that space. They're doing things like realigning the way that data is stored in heaps, so it's easier to share with other programming languages, right? And it also provides performance improvements as well, but that's by the by. Let me step over that one. Running out of time. Okay. Oh, excuse me. Right. So let's talk about AI and how that fits in and what that means for Java and the hardware time. What do you do, as an example, when one of these grids that you've got is so big and somebody says to you, I don't know what words are in it, can you go find them? Right? A type of problem that you might encounter. You could go off and find the biggest dictionary you've got and go scanning for it. But you might find that the person says, well, actually, they're not all necessarily spelled exactly right either. Just go find the words, right? This is the sort of problems that we have because data is never perfect. So what you do now is you teach neural nets, and you can go do this with these types of technologies. You teach neural nets to construct, right? What do? You teach it how words are formed by giving it a whole bunch of examples, and then you let it loose, right? And I first thought this, and I went, yeah, that's not going to work, is it? And the more I learned about this, the more I realized that actually, of course, it's going to work, because, in fact, it's going to be really easy. Anybody know what this is? It's a copyright statement for some piece of code. And here's the piece of code. Okay, it's C code, it's not Java code, but it's code, isn't it? Okay. This page and the page before were generated completely by a neural net. A neural network was taught what source code looked like, and it figured out it needed a header, and it figured out about comments. Actually not here, but it figured it all out, right? Trivially, you can go. There's loads of examples of this. You can go Google for this and go, oh, okay, do that myself. My point is that it's quite eminently possible. Really trivial to do these things, and because neural nets are such great number crunchers, and because GPUs are great number crunchers, that's what we're doing, right? So what you're expecting to see is GPUs being used to do more of the neural network processing. And because we've got Java models, because Deep Learning for J, etc., can create Java models, it's a much more possible for us to take that Java model that you create and push it down to a GPU without too much difficulty. And once we've got past that, what comes next? Well, these things. Neuromorphic processors. Neuromorphic processors are your brains in hardware. Right? These things have been around for a few years now. They're almost here. I mean, they're physically real. They are very, very low power compared to normal computers. They work like your brain. They are wired like your brain, which unfortunately means you can't think that well about them because they're totally event-driven. Right? Right? They're totally event-driven. Think about that. You're now moving from procedural to parallel to, well, beyond reactive, completely event-driven. Everything is event. You can't do it any other way. And because we've got the hardware, we've got GPUs in the data centers, you're going to get neuromorphic data, hardware in the data centers. They're real. So your learning thing is, if you haven't already got your head around these things, now is the time to start learning about machine learning, right? Because if you don't, you're going to get left behind, because this is what we're trying to achieve to make faster and easier. And then what comes beyond that? What's next? I should say, from an IBM point of view, in fact from an industry point of view, any hardware ideas that come up that we can figure out how to get into a data center, we will put the JVM on top of, or we will put inside. We will have co-processor type ideas where the Java VM is going to be talking to something else, right? So that means that the programming models that you create are going to be that different. You're going to be learning to have to solve problems differently because your procedural approach, even your multi-threaded approach, isn't going to work. It does not scale, it does not translate. But that's nothing, because then we've got this thing. Right, so there was this great guy, Lou Grosvenor, who said, if somebody was to build me a computer of the right design, I could solve search algorithms in a fraction, i.e. that line, of what they're normally done, i.e. that line. Right? That would be really cool. And this guy, well, his wish was satisfied by one of these things. Okay, anybody here have a clue what this might be?
Quantum mechanics.
Yeah, leave the room, thank you. So, this is a qubit. So your old bits, on or off, are now qubits with on or off-ishness state, and also they have rotational states and phases and things. Okay, I am not a quantum computer scientist. I have spent a lot of time with them, and I have a guy who sits not close to me, that far away from me, And we have lots of conversations about them, and I think I've got it, and then I walk away, and then like Chinese meals afterwards you go, no, I didn't get that. Let's talk about, if whatever I did to explain it to you in detail would be wrong, so I'm going to tell you what they are, and then a little bit example, right? This is the hardware. See, it's gold. It's lovely. So each of these little vertical things are microwave conductors because they're conducting microwaves all the way down to some things at the bottom. Here's another way of looking at it. So IBM and others have been producing quantum computing because we can. It's feasible, it's possible, and it has enormous returns. What you have is, almost all of this is the biggest fridge ever. Because the actual chip is a tiny thing, and I'll show you a picture in a second. That chip has to be running colder than space, because otherwise things don't work. It's interesting to see that as computers, we know that when they get hot, they can misbehave. With quantum computers, they only have to get a tiny thing, tiny microkelvin rise in temperature, and they give bad results. So all of this is about keeping it cold, as well as getting down to this thing. So qubits are where the action happens, and there are these little waveguides. So you've got to take a thing, and you've got to get it to behave in this quantum manner. And so you can't interact with it in any other way than sort of remotely. So you have all these microwave resonators to allow you to talk to this thing, which is happening at micro Kelvin temperatures, 0.0 something, right? That's the thing. But currently, there's 4 on there, but to give you an example, so we've just announced 50. 50 qubits is the power of the biggest supercomputer you can name. 50. So there's 4, 50. 60 qubits, 10 more, is considered to be more power than all the computers in the world today. Right? So this thing, because of its intrinsic parallelism, solves all problems at the same time. And I'll give you an example in Java in a second, just to make you think about it. The value to the world is, well, we can crack your encryption, okay? But the good news is if we did crack your encryption, there's quantum encryption coming, which if you use that is uncrackable at all. So that'll be cool. You can go play with one of these right now. You can go to the Quantum Computing Experience, just Google for it. You can write quantum computing programs and have it run on here, okay? But it won't work the way you think you would expect it to do. There's a battleships game you can play, but it doesn't tell you whether you sunk my battleships. It says, there's a chance you may have hit it, right? Or maybe you didn't, and you have to deal with uncertainty. You have to think differently. And of course, there's a cat in there somewhere. So just to wrap up, look what happened. So if I go back to this grid, so this is probably the best analogy I've got, but it's not going to explain to you how quantum computers work in any detail. It's just to give you a sense of the difference. So you're going to pick, you want to try and find the word Java. So let's try it differently. So we're going to do random search. Now, if you're doing a random search, right, the chances are you're going to have to hit half of them on average to find the word, aren't you? So you pick some random place and some random direction, okay? And what would you do if you were just doing it, you just repeat and repeat and repeat. Worst case, you could hit every single element before you found the word. And in fact, if you wanted to prove the word wasn't there, you would have to do that. Quantum computing comes back and lets you know, okay, oh, that one's good, okay. Hey, quantum computing, haha, right. So let's go with that one. Okay, so this quantum computer tells you not that you were right or wrong, but that you were rightish. And this one obviously tells you that you were way off. Okay, so you try again because you've got some feedback, right? And now you try somewhere else on that grid, right? And it comes back and goes, yeah, close, right? Well, this one's perked up, okay? And you continue, okay? And eventually, you might not get the exact answer, but you'll get really close. Is that better? Oh, I can hear myself. So go back. That's a word search example, don't worry about that. That URL, if you want to go play with quantum computing, you can do it right now. You can go off and either do a graphical thing, or you can actually write assembler code if you want, and you can submit it to a real quantum computer, and you'll get some results back. Sometimes it's not instant because there's a lot of people doing it, and if it's having an off day because it's warm, then you won't get the answers back. Right? But the reality is it's there now, and it's coming really quickly. Right. So I think I've said all this. My point has always been with quantum computing and neomorphs and all these things is that you have got to change the way that you're thinking, and your job is changing because you have to rise to the new requirements, which isn't writing web pages. We're still writing web pages, but it's so much more about these other technologies that you have to use. And the JVM, by getting the right hardware underneath and figuring out how we give you new models, so your Java language may not be Java language in 10 years' time, it can be something else, but by giving you the new models, we can generate it. That design allows us to do that. So all these characteristics about Java, the fact that it's runtime, the type safety, all these things, that's why we're still here. We're still doing all this, not because it's just because fun, but it is fun, but we do all this because it's the best place to put our investment to get the maximum effort and results out of the hardware that's changing. Right? But the change for you is you've got to start changing the way that you design applications and systems. Right? And I think that's probably about it. Yeah. I hope that's interesting. We are taking the JVM to different places. People say, oh, okay, Java's old. Well, Java might be old, but Java can get revitalized. We can put new language in the VM. It's the virtual machine in all of this that makes the big difference, which is why everybody is still here and investing in this. We're taking it to different places, and I hope you come with us. And that's it. Thank you.